Welcome to the Merlin Metro News Network. Our goal is to bring you programs that will help you to maintain the Merlin and Metro aircraft in the safest and most efficient manner. We'll cover a variety of subjects, each carefully chosen and developed to provide mechanics with the type of information they need. Each program has been developed by personnel with a combined experience of more than 30 years in maintaining Merlin and Metro aircraft. And these programs are being presented from a mechanic's point of view, with the problems in mind that a mechanic faces during his job. In addition to the video programs, we'll show you a means whereby you can receive factory accreditation for your knowledge of the Merlin and Metro aircraft. As you progress, 4 levels of accomplishment can be achieved. The top ranking is Quad M, Merlin Metro Master Mechanic. The requirements to achieve this designation are high, as many may never make it. But those who do will have the satisfaction of knowing that they are the tops in their field. Our program today covers the Merlin and Metro Technical Manual System with special emphasis on the wiring manual. Now we'll discuss the ATA 100 system of categorizing the subjects covered in the manuals and how it can help you. We'll also cover a brief review of electrical principles and concepts, since the next 4 programs will deal with the electrical system. And we'll be back here during the program to show you some other features and subjects that you'll find of interest. So sit back, relax, and let's roll our first program.
Aircraft maintenance is an important side of the aviation industry, and a side that most passengers never see. Passengers only see the bad side, such as when an aircraft is delayed or canceled. But the safety of aviation is largely dependent upon the quality of maintenance that is performed. The aircraft mechanic is the very foundation of aviation maintenance, and the person most responsible for ensuring safe maintenance. It is the high standards and integrity of the aircraft mechanic that ensure aviation safety. Modern aircraft have achieved high levels of performance and efficiency, but these performance gains have generally brought with them an increase in the complexity of modern aircraft. As some of the highest performers in their class, the Merlin and Metro series are also some of the most sophisticated aircraft in their class. This high technology challenges the mechanics that maintain the aircraft to be on their toes constantly. No matter how experienced a mechanic is, he could never remember all the information necessary to maintain an aircraft of this category. That's where manuals come in. The Merlin and Metro series of aircraft technical documentation consists of 8 large manuals. Within these manuals are a vast amount of technical information and data. There is so much data that just developing a way to index and categorize it so that a mechanic can easily find what he is looking for is a major effort. That's why a standard called ATA 100 was developed. ATA, the Air Transportation Association, realized early on that as aircraft became more complex, so would the technical documentation. They also realized that if each individual manufacturer was allowed to develop their own system of organizing and arranging technical data, mechanics would constantly have to learn and adapt to new systems. For these reasons, they developed Specification 100, which divided the systems likely to be on board an aircraft into logical groupings and assigned a number to each. Since this numbering was to be universal, consistency would result. Thusly, ATA Chapter 28 referred to the fuel system, whether the aircraft was built by Boeing, Douglas, or Fairchild. Subgroupings, the second 2 digits within the ATA numbering system, were also developed, so that while Chapter 28 refers to fuel, Chapter 2810 refers to fuel storage devices. These groupings and numbering system have brought order and logic to aircraft technical documentation. A complete listing of these numerical designations has been provided with a study guide accompanying this program. Like most other modern aircraft, the technical manuals for the Merlin and Metro series follow the ATA 100 format. To the mechanic, ATA numbering has several positive advantages. Data is easier to locate in the technical manual when the system involved is known, and the ATA designation assists in the troubleshooting effort when the system causing the problem is known. About the only problem that exists is when there is overlap between several ATA chapters. Here's an example of ATA overlap. This engine is defined under ATA Chapter 71, while this engine overheat detector falls under Chapter 26. This tube that carries bleed air to the environmental system is part of Chapter 21. Now, if we had a bleed air leak that causes the engine fire warning light to illuminate, there is obviously some overlap between all three chapters, 71, 26, and 21. Overlap can be overcome by remembering this simple concept. Always go to the ATA chapter that covers the cause of the problem, not the symptom. Of course, in some cases you may have to start with the chapter that covers the symptom in order to figure out what the cause is. But ultimately, you must get to the cause chapter if you are to find helpful information in the manual. While the ATA numbering system is important to all technical manuals, it is perhaps most important in the wiring manual. This large book of schematics would be practically unusable if it were not thoroughly and logically divided. The basic ATA numbering system is followed throughout, as well as standard aviation wiring diagrams, symbols, and terminology. Simplified block diagrams are included with complex circuits to aid in troubleshooting. To the maximum extent possible, each diagram covers only one system, with connections to other systems shown for clarity.
The technical manuals that support these aircraft require a lot of time and effort to produce. So let's take a look at the process. The process starts here with technical writers. Most of these writers were chosen from the production floor, where their valuable hands-on experience can help them to write manuals from a mechanic's viewpoint. Engineering drawings and specifications are used to obtain facts and data. All of the data produced is entered into the computer system for ease of future updating. Illustrations are created to support the technical manual using a combination of engineering drawings and photographs of the actual aircraft. An editor and senior technical writer will oversee the merging of words and illustrations together to ensure that the finished document is accurate and easy to use. After careful review and approval, the data will be printed and distributed to the field. The illustrated parts catalog and wiring manual are now almost entirely computer generated. This ensures accuracy and helps to allow more timely revisions. In all, the combined efforts of over 30 people are required just to maintain the technical documentation system. We know that the majority of people watching this program do not consider themselves to be aircraft electricians. If asked, most of you would probably answer, electrical squawks are a Sparky's problem, and I have no intention of working on them. Well, after the next 4 programs, electrical squawks will still be Sparky's problem, and you probably still won't be working on them. But we hope you'll have a better understanding of the electrical system, and especially how it affects other systems on the aircraft. If you look around the Merlin and Metro aircraft, it's hard to find many systems that don't tie into something electrical sooner or later. Now, if you don't have at least a fundamental understanding of the electrical system of this aircraft, you're going to have a hard time troubleshooting and maintaining the remaining systems on the aircraft. To help you understand the next 4 programs, we're going to have a simple review of electrical principles. Now, even if you're absolutely convinced you cannot understand electricity, stick around. You may be surprised to find out how simple we've made it. And if you're already knowledgeable on electrical principles, you might just find that some of our explanations are interesting, even humorous. Now remember, we're not trying to teach people to become electrical engineers, just how to deal with a subject that crosses the average mechanic's daily routine.
The Merlin and Metro series of aircraft have extensive electrical systems. Almost every facet of the aircraft's operation is in some way dependent upon a part of the electrical system for proper operation. And yet, as important as the electrical system is, if you were to ask the average mechanic what system they knew the least about, the answer would undoubtedly be electrical. There are 2 primary reasons why most mechanics feel this way. First, electricity is invisible. Since mechanics can't observe its workings visually as they can a mechanical system, They assume that its operation must be a form of semi-black magic. The second reason why most mechanics have a difficult time with the electrical systems is that they have been preconditioned to believe that understanding these systems is complex and requires extensive specialized training. These assumptions have made electrical systems into a maintenance problem, and unjustifiably so. In reality, most of the electrical systems of the Merlin and Metro aircraft are simple. Even the most complex electrical systems on the aircraft are easily understandable if the mechanic will break them down into smaller subsystems and analyze each of those individually. In order to proceed, let's consider a few electrical fundamentals. First, electricity. Suppose we could see it. What electricity really equates to is power. It is power that always wants to move in a complete, unobstructed route, a complete circle. It comes from a source and goes back to the source. Wires and conductors provide the roadmap for the electricity's route, hence the origin of the word circuit. Along the way, we can use this power to do work. Work might be moving an actuator or illuminating a light. The device supplying the electricity we refer to as the source. The device consuming the electricity we call the load. The electrical sources on board the Merlin and Metro aircraft are the batteries and the generators. Now, of course, there are a few more components involved in the electrical system and some principles unique to electrical circuits. Let's look over a typical wiring diagram and discuss some of these devices and the principles that allow them to work. Most of the components of electrical systems do one of three things: supply electricity, control electricity, or use electricity to do work. Of course, miles of wires are used to connect the various components together. While only acting as a means for electricity to travel from component to component, wiring and electrical connectors are no less important in the electrical system. In fact, the majority of electrical problems that occur involve wiring or removable connectors. The function of some electrical components is fairly obvious. Switches are a control device and stop or allow electricity to flow. Probably the most frequently seen devices are relays. Relays are used to connect or disconnect segments of an electrical circuit when told to do so. Relays functions are a property that occurs when electrical current flows through a wire. Passing an electrical current through a wire creates an invisible field around the wire. This field is weak and for all practical purposes undetectable. But if we concentrate the length of wire into a small area by winding it around a core, we concentrate the invisible field as well. Now the effects of this invisible field can be seen and can be put to work. This property of electricity is used in several circuits and many electrical devices. From the foregoing example, you may have realized that we've turned our wire-wrapped nail into a magnet. Electricity and magnetism are close cousins. Electricity can be used to produce magnetic force, and magnetism can be used to produce electricity. We're not going to try and go into the complex laws that define and govern how these forces interact, but should you desire to delve deeper, a bibliography included with a study guide for this program lists books that contain more detailed information. Another frequently used electrical device is the diode. This device is probably the simplest electrical component to understand. It allows electricity to flow in one direction and not the other. In a hydraulic system, a one-way check valve performs exactly the same function as a diode. In fact, schematic representation of a diode even shows which way it will allow electricity to flow. Transistors are another frequently used device in Merlin and Metro circuits, and one that often intimidates mechanics. And yet they each served as part of a mechanical transistor every day. Think of the water pressure in the pipes behind this sink as electricity. If we tried to regulate it with our hands, we'd all soon be pretty wet. But using this simple handle, we can regulate the water flow from full on to full off, and any place in between. That's all a transistor does with electricity. And in fact, in most applications on the Merlin and Metro aircraft, you don't even have to worry about this regulating ability, because most transistors are being used as electronic switches. They stop current flow until commanded, and then turn fully on to allow maximum current flow. Other primary electrical devices include sensors, which react to some external action by stopping or allowing the flow of electricity. The flow of this electricity may be used to indicate to the pilot that some action has taken place. While the entire electrical system contains hundreds of components, their individual operation is still relatively simple.
Well, how are we doing? We promised this would be a simple explanation of electrical systems in plain English, and hopefully we haven't lost anyone up to now. Now, earlier we said there were miles of wiring connecting the various electrical components together. Let's take a look at the buildup of the wiring harness. After the wires have been marked with the proper wire numbers, they are laid in on a series of mock-up boards. Now, these mock-ups allow the wire lengths and routings to be determined. Connectors are added to the wire harness while it is being built up. The completed wire harness will then be sent to the factory for installation in a fuselage. In our final segment of this program, we're going to show you how you can pick up clues about the operation of an electrical system by using the wiring diagram manual.
In our last segment, we said that most electrical components could be divided into three major groups: those that produce electricity, those that control electricity, and those that use electricity to do work. One feature of aircraft electrical schematics that often confuses mechanics is the use of the aircraft structure for a means for electricity to return to the source. Earlier, we said that electricity flows in a circular path from the source to the load and back to the source. In order to save weight and reduce the complexity of electrical circuits, the aircraft structure is used to provide the return path from the load back to the source in many circuits. A connection to the aircraft structure for this purpose is shown with the ground symbol. Let's take a simple circuit in the aircraft to illustrate some basic electrical principles. We'll use the cockpit fresh air fan system as an example. The power source is the circuit breaker in the cabin. Control devices are a switch in the cockpit and a relay. A switch in the nose wheel well is used as a sensor, while the fan motor itself is the load. The switch in the cockpit actually controls the relay, which in turn controls the operation of the fan. This is an important concept in electrical circuits: nested controlling. One device controls another device, which may in turn control other devices. This type of interaction is used for several purposes, sometimes to make actions take place in a predetermined order. While this circuit may seem so simple as to be obvious, it illustrates the concepts that must be mastered to successfully troubleshoot electrical systems. Let's look at the circuit from a function standpoint. We want to allow the pilot to be able to operate the fresh air fan when needed. We also know that the fan should not operate in flight if the aircraft is pressurized, so we would like for it to turn off automatically in flight if the pilot forgets to do so manually. We must, however, allow the pilot the ability to manually override this automatic shutoff feature should an emergency arise. We therefore have three controlling functions necessary: fan on or off normally, fan off automatically, and fan overridden to on. Now let's discuss three other important concepts of electrical circuits: that are shown in this example. The first is sequence. In our fresh air fan circuit, the sequence is as follows. First, the cockpit switch is moved to the on position, then the relay closes, then the fan operates. Other systems in aircraft, most notably hydraulic, use sequences, but almost every electrical system has a sequence of operation. Understanding, and most importantly, troubleshooting the circuit, requires that you thoroughly recognize and understand the sequence of events that must occur if the system is operating properly. The second concept is called equivalent paths, or common functions, parts of the circuit that achieve the same result, but through different means. If we look at our fresh air fan circuit, the normal and the override position of the cockpit switch both should accomplish the same thing. The fresh air fan should operate. The difference between the two paths is that the normal system includes the nose wheel well switch, while the override path bypasses this switch. If the pilot were to write up that the fan is inoperative in the normal position, the first thing to do would be to try the override position. If the fan now operates, we of course know there is a problem with the switch in the nose wheel well, or its wiring. But even if the fan doesn't work, we can now be reasonably certain that the switch in the nose wheel well is not the problem. This is a crucial element of why some people can troubleshoot electrical systems so much faster than others. Look for the equivalent paths, or common functions. Use parts of the system to check other parts of the system, and identify those components that can't be the cause as quickly as possible. Study the wiring diagrams of the system you are working on carefully to locate the equivalent paths, and use them to save yourself time and effort. The third concept is the logic of the circuit involved. Consider our simple fan circuit. If the cockpit switch is moved to on, and the nose gear is not retracted, the fan is allowed to operate. If the nose gear is retracted, the fan is not allowed to operate. If the cockpit switch is placed in the override position, the fan is allowed to operate, and the position of the nose gear is not considered in the circuit. These logical steps were what the design engineer originally used to develop the circuit. In order to troubleshoot and repair this circuit, you must be aware of this logic. Countless hours of work and frustration are expended by mechanics every year trying to repair electrical circuits that were already working as designed. You will find that the simplified block diagrams included with most of the larger electrical schematics are a powerful aid in determining the logical operation of the circuit.
You're probably wondering why we're spending so much time on the fresh air fan circuit. It doesn't cause many maintenance problems, and it's so simple that even a non-electrician like myself can understand it. Well, we chose that system because it is simple, and yet it gives us the opportunity to throw some very important concepts at you. Now, when a circuit as simple as the fresh air fan, you can understand it without thinking in any kind of logical or methodical fashion. But in some of the next programs, we'll be getting into the starting and generator systems, as well as SAS and battery fault. In circuits of that level of complexity, you must work and think in an orderly and step-by-step fashion. And if you'll do that, these larger systems will be just as easily understood as the fresh air fan circuit. We hope you've enjoyed this first program and look forward to our next. Until then, good flying and good maintenance.